Now let's continue on looking at simple random sampling. Now you'll recall that the purpose of sampling from a population is to learn something about the population and to be able to answer questions about the population. We do that by calculating one or more statistics from the sample and then using those statistics to draw inferences about the population. Now, what we're going to be focusing on right now is how to make inferences about a population mean using a simple random sample. Now, to do that, we're going to first calculate the mean of the simple random sample. And then once we have that sample mean, then we have to be able to use it in order to make an inference about the population mean. Now, to use the sample mean to make an inference about a population mean, we have to know something about its sampling distribution. You'll recall that we've been talking about this quite a bit in previous modules. And so we're going to first consider characteristics of the sampling distribution of the sample mean. And in particular, we're going to be considering the mean of the sampling distribution of the sample mean. So let x1, x2, and so forth up to x sub little n be a simple random sample of size little n from a finite population containing capital N values, with population mean and population variance denoted by mu and sigma squared, respectively. Now, denote the mean of the sampling distribution of the sample mean by mu sub x bar. All right, so x bar is the sample mean. It is a statistic, it's a random variable, and it has a probability distribution. And that probability distribution is called its sampling distribution. That sampling distribution has characteristics just like any other population or distribution. In particular, it has a mean. All right, and we're interested in determining what the mean of the sampling distribution of x bar is under simple random sampling. And so let's first denote the mean of the sampling distribution of x bar under simple random sampling. And so we will denote that by mu sub x bar. So this is just, this means it's the mean of the sampling distribution of x bar. Now it turns out that mu sub x bar, the mean of the sampling distribution of x bar, which we could also denote as the expected value of x bar, is just equal to mu, the mean of the underlying population. All right, and so it follows then that the sample mean x bar is an unbiased estimator of the population mean under simple random sampling, just as it was under IID random sampling. All right, you'll recall a similar kind of result that holds when we are performing IID random sampling. Okay, and so we see that we get the same result here when we're performing simple random sampling. And so the sample mean will therefore be used as an estimator of the population mean. And we're going to start using the following type of notation for estimators. Since the mean of the sampling distribution of x bar, the expected value of x bar, is the underlying population mean mu, and you'll remember that when we're doing statistics, we're having to make inferences because we don't know the true value of mu. We're having to estimate it. All right, and so we're going to denote the estimator of mu by mu hat, and because the mean of the sampling distribution of x bar is mu, all right, we're going to denote x bar by mu hat. So this is just telling us, okay, that in future slides, when we see mu hat, we are referring to x bar. This is just a little bit more general way of denoting an estimate of the population mean. Okay. All right, now we're still considering the sampling distribution of the sample mean x bar, but now we're going to be considering the variance and the standard error of the sampling distribution of x bar. And so again, let x1, x2, and so forth up to x sub n be a simple random sample of size little n from a finite population containing capital N values with population mean mu and population variance sigma squared. Now denote the variance of the sampling distribution of the sample mean by sigma squared sub x bar. We can also denote it as var, or variance, of x bar, right? So we'll use both of these notations. And it turns out that under simple random sampling, the variance of the sampling distribution of the sample mean, x bar, is equal to this expression here, which involves the population size, the sample size, and the variance of the underlying population. And so the variance of the sampling distribution of x bar is equal to capital N minus little n all over capital N minus 1 times 1 over little n times sigma squared. Now that we have this formula for the variance, the true variance of the sampling distribution of the sample mean, then to find its standard error, which you'll recall is the standard deviation of the sampling distribution of x bar, we just take the square root of this expression. All right, and so we will use the following notation for the standard error of x bar. Sigma sub x bar, right? We can read this as the standard deviation of the sampling distribution of x bar. We'll also use this notation here, SD for standard deviation of x bar. And so it turns out that that is equal to the square root of that expression that we've got here. Now we could, in this case, pull the sigma squared out after we've taken the square root, and so we could express it this way as well. Now one thing I want to point out is that you'll recall, think back to IID random sampling, and think back to the sampling distribution of x bar, the sample mean, and in particular think about the variance of the sampling distribution of the sample mean. Note that under simple random sampling, the variance of the sampling distribution of the sample mean is different than what it is under IID random sampling. Under IID random sampling, this last part of the expression here, under IID random sampling, this highlighted piece is the variance of the sampling distribution of x bar. But when we're performing simple random sampling, we have to adjust that using this multiplicative, this factor here, all right? And so what we're seeing here is the variance of the sampling distribution of the sample mean is different under under simple random sampling as it is, or than it is, under IID random sampling. And because the variance of the sampling distribution of the sample mean is different, so is the standard error. All right, and so we're beginning to see why it's important that we understand the way that a population is sampled, because that's going to determine formulas for things like the variance, the standard error, and so forth for various summary statistics that we compute from the simple random samples. Now let's look at another example. So again, consider this population of 6 values, 10, 3, 18, 32, 15, and 27. And what we want to do is to compute the mean and the variance for this population. All right, and then after we do that, we want to construct the sampling distribution of the sample mean for simple random samples of size little n equal to 2. And we want to answer some questions about that sampling distribution. In particular, what is the mean of the sampling distribution of the sample mean for simple random samples of size little n equal to 2, and also what are the variance and standard deviation of the sampling distribution of the sample mean for samples of size little n equal to 2 under simple random sampling. Now the first thing we'll do is calculate the mean and variance of this population. And so the way we do that is, again, to add up the values in the population and then divide by capital N, which is the number of values in the population. So if we add up those values, we get 105. There are 6 values in the population, and so the mean of the population is 17.5. Once we have that, then we can calculate the population variance. To do that, what we do is we subtract 17.5 from each of the values in the population. We square those values, add the squared deviations up, and divide by capital N, which is 6. All right, and so the sum of the squared deviations from each of the values in the population from the mean is 573.5, and we divide that by 6. Okay, and so we get a population variance, which can be expressed in a variety of ways. 95.58, and then the decimal 3 is repeating there. We could also represent that as 95 and 7/12 or 1147 over 12. So I've got these, I'll probably be using each of these three representations throughout some of the rest of the examples. All right, but those are the values for the mean and the variance of this population. And if we wanted the standard deviation, all we would have to do is take the square root of this variance. Okay, now we want to consider simple random samples of size little n equal to 2. And what we want to know is, what is the mean of the sampling distribution of the sample mean for samples of this simple random samples of this size? And also, what are the variance and standard deviation of the sampling distribution of the sample mean for samples of size little n equal to 2, again, where we're performing simple random sampling. Now, we have seen our 30 possible samples. I've got them listed here. I've added a column to my table, and so what I'm going to do here is I'm going to calculate the sample mean for each of my 30 samples, right? This is similar. This is just like the example that we did back in the module on IID random sampling. And so we're going to calculate the sample mean for each of the 30 samples, and then we can calculate the mean and the variance of this list of values, and that will give us the mean and the variance for the sampling distribution of the sample mean for this situation. Samples of size little n equal to 2, where we're performing simple random sampling. Okay, so here are the sample means. All right, you see all 30 of them there. And when we calculate the mean of those values, the mean of that column of data, we get 17.5. Okay, so that 17.5 is the mean of the sampling distribution for the sample mean for simple random samples of size little n equal to 2 from this population of 6 values. Now, we can also calculate the variance, the population variance of this list of values. And when we do that, we get 38.2333, which is equal to, that's a rounded value, right? The variance of that, the population variance of that list of values is 1147 over 30. Okay. Now, we've created this table in a word processor, but we could also do this in the context of a spreadsheet. In fact, that would be much preferable. All right, and so here is a display of doing that. I've used a spreadsheet. I have typed in the sample number and the values for each of the 30 samples, and then I've programmed the cells in the spreadsheet to calculate the sample mean, the sample standard deviation, and the sample variance for each of the 30 samples. All right. We've also got up here, we see the population of 6 values, and then we've calculated the population size, which is 6, the population mean, which is 17.5, and the population variance, which is 95.5833, rounded to 4 decimal places. Okay. At this point, we're interested in this column here that I've got highlighted, right? That column contains the values for the sample mean for each of my 30 samples, and down below here I've calculated the mean of that column of data, the population variance of that column of data, and then the standard deviation. Okay, and so you see here that with the spreadsheet we also get 17.5 for the mean of these values, and we get 38.2333 for the variance. Right? And so based on this empirical calculation, the mean of the sampling distribution of the sample mean is 17.5, and the variance of the sampling distribution of the sample mean is 38.2333. Okay, so again, from our empirical calculations, mu sub x bar is 17.5, and sigma squared sub x bar, which is the variance of the sampling distribution of x bar, is 38.23. So this is what we get empirically, all right? Now, what the theory tells us should be the case is the following. Based on the theory that we just stated previously, the mean of the sampling distribution of x bar should be equal to mu, the mean of the underlying population, which was 17.5. We calculated that a few slides ago, and that's indeed the case, all right? In addition, the theory tells us that the variance of the sampling distribution of x bar is given by this expression, which involves the population size, the sample size, and the underlying population variance, which was 1147 over 12. All right, the population size is 6, the sample size is 2. And so when we do that calculation, we get 1147 over 30, or 38.2333, and so forth. So we see here that what we get empirically is exactly what the theory tells us we should get. All right, and that's going to be the case always. Now, let me just point out that this is not a proof of that result in general. It's just a demonstration that the theory holds in this particular example.